Today's notes are on polynomial division and real zeros. So two topics here, and you'll see the notes are split into two sections. So we'll jump into the first example. In first example, we have a polynomial function. As we saw from what we did in the last unit, we know if we want to try to get an accurate graph of this, we want to try to factor what we have. Once it's factored, that'll give us our zeros. When we graph this, we know the general shape is going to start in the lower left corner, move up to the upper right hand corner. Now, what we're going to talk about today are just some tips to help us factor. So if you look at the directions here, it says show that x minus 2 is a factor. Now that's a good thing because we know one of the factors already. It's given to us in the directions. Okay, we're very fortunate to know that. If we don't know that, we have to find that. But since we know that, since we're given that, we can say, okay, it's going to break down as x minus 2 times something. Now we need to know what the something is. Now let's think about this. Now what factoring really is dividing. So if we were to multiply these terms together, we'd get what we had. If we were to divide this by x minus 2, we'd get this factor over here. So what we really want to do here is take our original expression and divide it by x minus 2. Now there's a few different ways you can do this. Probably the easiest way is a method called synthetic division. Now, oftentimes people don't like synthetic division because it doesn't make a whole lot of sense. But once the process is down, it's rather easy to do. Here's how we synthetically divide. We think, first, what is our 0? What can we plug in here to make this equal 0? And that number is 2. And in fact, if you want to test that, if you plug 2 in here in place of all these x's, you'll get 0. Okay, that's really what a 0 is. What number you can plug in to make that equal 0. So put that in front. We'll put the coefficients of our polynomial inside here. So 2, 1, -7, and -6. I'll put a segment down here with a little box for our remainder. Okay, so here's the steps for synthetic division. We always add straight down, so that gives us 2. And then once we have a number here, we multiply it by what's in front and put that number diagonally right here. So we get 4. Add straight down, multiply by 2 diagonally, add straight down, multiply by 2 diagonally, and add straight down. Now it is a good sign to get a remainder of 0. If you know this is a 0 and you don't get that remainder, it means you did something wrong. If you don't know it's a 0, this is a way of telling it's a 0. So the fact that we got a remainder of 0 tells us for sure that 2 is a 0 of this function. Okay, now what do these numbers down here tell us? Now those numbers are the coefficient of this other factor. So that gives me 2x squared plus 5x plus 3. Okay, now here's how that helps us. If we want to factor this completely, we know that this next trinomial, if it's going to factor, is going to factor as two binomials. Now, some people know different shortcuts to try to factor something like this. Some of those shortcuts sometimes work, some of those shortcuts don't work at all, and to be honest with you, I like to avoid those shortcuts because they don't always work for me. Instead, I like to use a little trial and error, some guess and check. We know that these first two terms are going to multiply to give us 2x squared. So one must be 2x, one must be x. We know that the last two terms must multiply to give us 3. We don't know if that's going to be 3 and 1 or 1 and 3. So let's just try one of those. So I'm going to say plus 3 and plus 1. And then we can test this by multiplying this in our head. So that would give us 2x squared plus 2x plus 3x. Hey, that's 5x plus 3. Hey, it does work out. So we chose correctly. If we chose incorrectly, we'd simply switch things around and we would know that things would work out. So since all this is saying is find the remaining factors, we have now completely factored this expression. So we're done. If we wanted to find the zeros, we could. If we wanted to graph this, we could. But at this point, all we need to do is find the factors. Okay, let's try one just like that. So we've got this new function. We know x plus 4 is a factor, and we know something else will be a factor as well. To find that something else, we're going to we're going to synthetically divide. So let's test this out. So Bring down that 2, multiply diagonally by -4. Add down, multiply diagonally. Add down, multiply diagonally. Good sign, we've got a remainder of 0. That means we're on the right track. So our remaining factor is 2x squared plus x minus 1. We now need to break this down, or attempt to break this down into two binomials. We know the first terms are going to multiply to 2x squared, so I'm going to go with 2x and x. We know the last terms are going to multiply to -1, so it's either going to be -1 and +1, or +1 and -1. I'm going to try +1 and -1. Let's see if that works. So if we multiply these together, we get 2x squared minus 2x plus 1x. Ooh, that does not work. I chose incorrectly. So let's just erase that idea. Let's erase these things we put in here. And instead of writing +1 and -1, let's try writing -1. Oops, let me get that black marker back. -1 and +1. Oh, now I'm confusing myself. All right, let's try that again. Let's go with -1 and +1. And if we test it again, we get 2x squared plus 2x minus 1x. Hey, that does work. -1. Okay, so we have completely factored, which means we are done with this problem. Again, we could go further. Our zeros we'd get from these x terms here. We know the general shape of the graph, so we could do a little more with this. However, all we're asked to do is find the factors. Okay, let's take a look at a little bit different kind of problem. Now, we need to divide this. So very similar to the last problem where we had to find the factors, except it's just saying, let's just divide these two right away. We don't even need to find all the factors. Let's just divide one by the other. I'm going to do things incorrectly to start. Okay, here's my 0 would be +1. My coefficients would be 1 and -1, so I can set this up using synthetic division. Here's the mistake. See how this is x to the 5th minus 1? What my coefficients really should be are 1x to the 5th plus 0x to the 4th plus 0x to the 3rd, etc., etc. So I'm going to erase this work that I've done here. I'm going to try writing this again with all those coefficients. So I put this problem here purposely to show you that there's a whole bunch of terms here. There's 1x to the 5th plus 0x to the 4th plus 0x to the 3rd plus 0x squared plus 0x minus 1. If there are missing terms, you have to put zeros in their place. Okay, let's run through the steps. Add down, multiply diagonally. Add down, multiply, add down, multiply, add down, multiply, add down, multiply. Remainder of 0, that's a good sign. So that means if we divide these two, here's what we get. We get 1x to the 4th plus 1x to the 3rd plus 1x squared plus 1x plus 1. So the key to this problem, we have to be careful. If we're missing different terms, we just need to put zeros in there. This is an extreme example, but if you're missing any term in here, we have to put a 0 in its place. What about this next one? Now what's different here is that, look what we're dividing by. It's not a binomial. We can't simply find a 0 to this by plugging some number in. If you ever get something like this, we have to resort to long division. Now, long division is a pain. No one likes long division. There's a reason synthetic division was invented. Even though it doesn't make a lot of sense, it is much, 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 much easier than long division. But sometimes we just have to use long division, like if we're dividing by something like this where we do not have a 0. To do long division, what we do is we write out what we're dividing, what we're starting with, I should say, and we're dividing by this trinomial, x squared plus x minus 1. And let's see if we can take care of this. So what we do is we say, what can we multiply this first part of this term by, this x squared, to get 6x to the 4th? And we can multiply by a 6 and x squared. So if we do that, 6x squared times this other x squared, that gives us 6x to the 4th. If we multiply by the next term, 6x squared times x, that gives me plus 6x to the 3rd. And if we multiply by this last term, 6x squared times minus 1 is minus 6x squared. And now we need to subtract down. I like to put this in parentheses to emphasize that we're subtracting. First term, no problem, that's gone. But negative x cubed minus 6x cubed is minus 7x cubed. Do not add down, we always subtract down. Minus x squared minus another minus, that's like plus this, will give us plus 5x squared. And I'll bring everything else down as well. Now you can already see why long division is a pain, and we'll keep going with it. So now we say what times x squared equals minus 7x cubed, and that'll be minus 7x. Now I need to multiply minus 7x by each of these terms, which gives me minus 7x cubed minus 7x squared plus 7x. Subtracting down, careful to subtract. The x cubes are gone. 5 minus a negative 7 gives me 12x squared. 9 minus 7 gives me 2x, and then minus 3. Okay, almost done here. Almost done. Now we need to say one last time, what times x squared equals 12x squared? That answer is 12. Multiplying 12 by everything gives me 12x squared plus 12x minus 12. Remembering we need to subtract down, gives me, well, the x squareds are gone, minus 10x, subtracting actually makes this a positive, so it gives me plus 9. Now we can't do that any further. Nothing times x squared is going to give me this, so we have a remainder. Now your remainder, your part left over, think about this. If we were dividing by 5 and you had 2 left over, you'd have 2/5 remaining. So it's like you have your remainder over what you're dividing by. So we have to say plus negative 10x plus 9 over x squared plus x minus 1. And there's your answer. And that, my friends, is not any fun. So hopefully we don't see too many of those. Okay, let's put that behind us. Let's move on. Now I told you there were two ideas to these notes. Here's the second of those two ideas. If we have a polynomial function of degree n, then you have at most n real zeros. So for example, if you have something like f of x equals 5x cubed plus etc., 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 then you have at most 3 zeros. And if you think about it, it makes sense. So this graph that comes up here, if you factored it, it could go through the x-axis in at most 3 different places. Now it doesn't have to have 3 zeros. Maybe it goes through the x-axis in just one place. It's possible for these functions to not have any zeros, or any real zeros, I should say. Now, here's what this rational zero test is. If we need to find these rational zeros, what we do is we say that these are all going to be of the form p over q, where p, this is going to be the factors of the last term. So take your last term here, let's say this last term was plus 10, all the factors of that are possible numbers we could have right here. Okay, q are going to be factors of the first term. So our first term here was 5, so any possible factors of that would be on the bottom of this. Now, it's kind of confusing until we see some examples. So we'll see some examples here in just a bit, but the guy who came up with some of this stuff was this man here, René Descartes, French mathematician, and notice it says French philosopher, so not just a mathematician, but a philosopher. Descartes combined algebra and geometry. So he was the first one to realize that, hey, these equations, if we graph them, they have geometric shapes. These geometric shapes, if we talk about them algebraically, we can come up with an equation. So he really put the idea of algebra together with the idea of geometry through graphing. And that's why the xy plane, the coordinate plane, is sometimes called the Cartesian plane. It's named after René Descartes. Okay, so here's something that he came up with, this rule of signs. So here's what it is. The number of positive real zeros. Number of positive real zeros. So you have some polynomial function. It has a number of zeros. Now, let's say you have something like y equals x to the fifth plus, et cetera, et cetera, et cetera. We know that this has at most 5 real zeros. Okay? How do we know how many of those zeros are positive, how many are negative? Well, the number of positive real zeros is equal to the number of sign changes of the function. Or it could be less than that. So I'm going to say or less than that. But if it is less than that, it's got to be by an even amount. And we'll talk about why that is here in just a bit. So, like I said before, looking at examples will make this make a whole lot more sense. So let's jump in. Next example here. How many positive and negative zeros are possible? Well, if we look at this function, we know the general shape's going to come up here, do something in the middle, we don't know what, and end up looking like this. We know the zeros are where this crosses the x-axis. Since this greatest power, the degree is 5, it could cross the axis in as many as 5 places. Okay, so the total number of zeros possible, it's got 5 total possible zeros. It doesn't necessarily have 5 real zeros, but 5 total zeros. How many of those could be positive? So how we find the positive ones, we look at the sign changes. So the first term here is positive, positive 3. Second term is a positive 2. Third term is a minus 5. This fourth term is a plus x squared. Last term is a minus 1. Now your sign changes occur right here is a sign change, here's a sign change, and here's a sign change. So it's where we have, don't worry about how many positives and negatives total, but where it changes from a plus to a minus. So since there were 3 sign changes, we have 3 possible positive zeros. That means that since there's 5 total, 3 are positive, that means there's 2 negative zeros. Okay, now something we need to address here as well. Just because you have this number 3, this number 2, doesn't mean you're going to have exactly 3 or exactly 2. It's possible some of these zeros are not real numbers. It's possible some of these are imaginary numbers. Now, we're not going to encounter any of those yet today, but if you do have these imaginary zeros, these complex numbers, we could have slightly less than 3 or slightly less than 2 positive or negative zeros. And it's always less than this by an even number. So I'm going to say 3 positive zeros, or we could have 1. 2 negative zeros, or we could have none. Okay, so anytime you have these possibilities, you could have an even number less than what you think these numbers are going to be. Okay, so let's try one of these here. Find the real zeros. So now we need the exact zeros of this. So we need to know what numbers we can plug in here to make this equal 0. There's 3 possible, so I'm going to write that to start 3 possible. If I look at sign changes, positive, positive, there's a sign change, there's another one. So 2 of these we're thinking are going to be positive. 1 of these we're thinking is going to be negative. The possible numbers are, remember, the factors of this term over the factors of this term. So the possibilities are like 3 over 2, or maybe 3 over 1, or perhaps 1 over 2, or 1 over 1. Now where am I getting those? The numbers on top are the factors of 3, so 1 and 3. Numbers on bottom are the factors of 2, so 1 and 2. Now these could be positive or negative. So here's the different numbers we could possibly have be the zeros here. So there's a number of ways we could find these. We could plug them all in, see which ones work, which ones don't. We could try to factor this. Let's do a combination of that. So I'm going to test some easy numbers here. So the number 1 is an easy one to test. So if we plug 1 in here, we get 2 times 1 is 2, plus 3 times 1 is 3, minus 8 plus 3. Does that equal 0? It does not. So 1 is not a possibility. Let's get rid of that work. How about negative 1? Is negative 1 a possibility? If we plug negative 1 in here, we get, let's see here, negative 1 to the third is negative 1 times 2 is negative 2. Negative 1 squared is 1 times 3 is plus 3. Negative 1 times 8 is plus 8, then plus 3. That doesn't work either. So let me erase that. And you know what? Now that I think of this, sorry if that was a little messed up there, but we've got these possible zeros. I plugged 1 in here and it didn't quite work for me, but I think I made a mistake here. Let's plug 1 in here again. 2 times 1 is 2, plus 3 times 1, minus 8 times 1 plus 3. This does equal 0. So that tells us that, and I'm going to get rid of this work here, that tells us that plugging 1 gave you a value of 0. So x minus 1 is a 0 of this function. Now we need to find out what this other factor would be. We can do that with synthetic division. So I'm going to set this up. And we know if we add down, multiply diagonally by 1, add down, multiply diagonally, add down, multiply diagonally, we get a remainder of 0. That's a good sign. But what that tells us is that 2x squared plus 5x minus 3 is also a factor of this polynomial. All right, I think we can break that down even further. I think we can break it down as two binomials. Now, some people have different shortcuts here to break these down. Some of these shortcuts are good, some are not so good. I prefer to avoid the shortcuts because sometimes they just don't work. Instead, I like to break this down by thinking what times what would give you 2x squared? It's got to be 2x times 1x. What times what is minus 3? Well, that's got to be plus 3 or minus 1 or minus 3 plus 1. So let's just try one of those. I'm going to try minus 1 and plus 3. And since we are doing a little guess and check here, we need to test to see if it works. 2x squared plus 6x minus 1x. Ooh, that does work. Minus 3. So it does work out here. I guessed correctly. Now this is the factored form of that polynomial. What we really want are the zeros. The zeros are the numbers we can plug in to make this equal 0. So if we plug 1 in here, we get a y value of 0. If we plug 1/2 in here, we get a y value of 0. And if we plug negative 3 in here, we get a y value of 0. So you can write your zeros this way. More often they're seen written in this format. The zeros are the following x values: 1, 1/2, and negative 3. Okay, now that's as much work as we'll ever need to do for one of these problems. So let's zip through one more of these. We'll go through kind of quickly. Same kind of problem. You might want to just pause the video and try this one on your own, but I'm going to take care of this pretty quickly here. We know there's 3 possible zeros. We know based on this one sign change that one of these could be positive and the other 2 could be negative. The possible zeros we might see are the factors of this last term over the factors of this first term. So possible numbers would be like 1 or 2 or 4 or 5 or 10 or 20. And this could be positive or negative. So let's just start with the simplest one, the number 1. If we plug 1 in here, we get 1 plus 8 plus 11 minus 20. Guess what? The number 1 works. So I'm going to erase my work here. Since the number 1 is a 0, that means x minus 1 is a factor. Now to find that other factor, we can use a little synthetic division. You could use long division, but no one would ever want to do that, I don't think. I'm going to avoid it if I can. Using synthetic division, I think you'll all agree, once you get used to it, is much simpler. Remainder of 0, that's a good sign. Our factor is 1x squared plus 9x plus 20. Okay, now this one's going to be a little bit easier to break down to factor than the last one, simply because your leading coefficient is 1. which means we can think, what are two numbers that add to 9 multiplied to 20? And I think you'll all agree those numbers are 4 and 5. So now that we've got it in completely factored form, our zeros are the numbers that you can plug in there to make it equal 0. And there they are. Now we could go further and graph this. We know here's your x-intercepts. We know this number up here is your y-intercept. We know the general shape of the graph is something like this. We could do all of those things, but we've already answered our question. Find the zeros. Okay, that wraps up our notes here. We've got an assignment to take a look at, so do what you can on this assignment. When you're done with this, we can move on to the next section, which is 2-4.